Hello, this is presentation 7, when we're going to present continuous simulation problem. I'm Shin and I'm in a team with Alana and Cisco. So what is continuous simulation? It is a model of a system that continuously tracks system response according to a set of equations involving differential equations. The set of differential equations can be formulated in a conceptual model with two approaches, the first being a deductive approach. The behavior of the system comes from a physical law that can apply. The other being inductive approach. The behavior of the system comes from observed behavior of an example.
The problem example that we're using is the predator-prey model. For this model, we're looking at the rate of growth and decline for the predators and the prey's populations. Both of these variables are dependent upon one another, so as the predators increase, you see the preys decrease, but as the prey decreases, you also see that the predators don't have as much food, so they'll eventually decrease as well. And it goes back and forth, fluctuating that way. XT we're using to represent the change of prey population over time, and YT we're using to represent the change of predator population over time. The principles that we used to construct the problem were figuring out the differential equations that were needed to show the change of populations for both the prey and the predator, and also how many interactions were made between the predator and prey, and then also figuring out the starting population of the prey and the predator. So the things that we had to initialize were the growth rate for the prey in absence of the predator, and the death rate of the predators, the prey caught per predator, and the predators born per prey caught.
So for the prey and predator model, we used MATLAB to write the code in. We have 4 parameters, being B, the growth rate of prey in absence of predators, D, the death rate of foxes, P, rabbits caught per fox, and RX, foxes born per rabbit caught. And then we're going to run it 10,000 times. And under population start, we'll have an array of zeros for both prey and predators, and they will fill up as the for loop runs through each differential equation for each population. So as I said before, we're going to have a for loop going from 2 to 10,000, and then for the set of equations, we have one for the prey population and the one for the predator population. So for the first one, x of t for the prey population equals the population of the previous time plus the growth rate of the prey in absence of predators times the population in the previous time minus the rabbits caught per fox times the population of the predators at the previous time times the population of the prey of that previous time. And then for predators, y of t equals that population of the t minus 1, meaning the previous time, plus the foxes born per rabbit caught times the rabbits caught per fox times the population of the prey of that time times the population of the predators of that time, all of that minus the death rate of foxes times the population of the foxes themselves. As you can see the results from the MATLAB code of the prey and predator model here on this graph, as time passes by until the 10,000th occurrence of them meeting, the prey population is red and the predator population is seen in green. And as you can see, the prey population starts at 500 and the predator starts at 250. So as the prey population increases, so does the predator population. But as you can see, the predator population is increasing, the prey population decreases, and so forth. And that happens throughout each occurrence, as you can see, and they fluctuate proportionally depending on the increase and decrease of either the prey population or the predator population. when searching for methods to optimize continuous simulation problems, such as the prey and predator model or any other type of model that may be a continuous simulation model, I found like two methods, which is the stochastic optimization, which basically this model forecasts the probability of various outcomes under different conditions using random variables. And secondly, the second method is gradient-based method, which is a simpler one, which is this method solves problems using search direction defined by the gradient of the function at the current joint. So these are two methods to optimize continuous simulation problems and try to find the best or the optimal solution or best solution to display them.